Welcome back, people. This week we're going to talk more about the K-Cup and what's inside the K-Cup, the design, the materials, filters, patents, and the decisions that shaped it. In the last episode, we covered the Keurig story and how the K-Cup became the default single-serve system in America. Today, we're going to go one level deeper because what it looks like, a simple plastic cup, it's actually a carefully engineered single-use brewing device. We're going to talk about the design, the materials, the filter, the piercing zones, the patents, and some decisions that, in hindsight, even the inventor regretted. So before we get into it, please subscribe. As I've said before, it costs nothing and just helps the algorithm that will get this content to more people who might be interested in this. So what is a K-Cup actually designed to do? A K-Cup is not an espresso capsule. It's a mini filtered coffee system designed to make a predictable mug of brewed coffee with zero effort from the user. To do that reliably, the pod must control how much water enters, how the coffee is contained, how the flow is managed, and how the liquid exits, all at low pressure, high speeds, and of massive scale. So think of the K-Cup not as packaging, but as a disposable drip brewer. At its core, a K-Cup has four functional elements: a plastic cup body, a top lidding film, an internal filter, and a bottom piercing zone and exit zone. Inside the pod, the coffee sits inside the filter. The water enters from the top, passes through the coffee, and exits through the bottom. Everything happens inside a closed cartridge. One thing people always notice is the empty space at the bottom of a K-Cup. That space is not wasted, it's deliberate. It acts as a hydraulic buffer zone. It allows clean piercing without shredding the filter or destroying the filter, controlled outlet formation, and settling of fines away from the cup. Tolerance to variations in fill weight and grind, and without that space, flow becomes unstable, filters could tear, fines escape, and cups become inconsistent. It looks inefficient, but it's one of the reasons the system works. Early K-Cups were made primarily from polystyrene, not because it was fashionable, but because it offered stiffness, dimensional stability, heat resistance, and a good freshness protection. At the time, it solved the problem Keurig cared most about: consistent brewing with a long shelf life. Later, design shifted materials for recyclability and perception, but the early choice was a classic engineering trade-off. Another key choice in the design was thermoforming. K-Cups are typically thermoformed from a sheet, not injection molded. Why? Because thermoforming is faster, uses less material, has a lower tooling cost, and is ideal for thin-walled disposable cups. Injection molding is excellent for rigid, reusable parts, but for billions of disposable parts, thermoforming wins almost every time. If you want to understand K-Cup performance, we also have to look at the filter. The filter holds the coffee, controls the fines migration, defines flow resistance, and determines the contact time. It's usually paper or a non-woven material, and crucially, it is fixed in position. It's not loose. It's heat-sealed, bonded, or mechanically trapped to form a defined internal basket. If the filter collapses, shifts, or tears, the flow goes wrong, the coffee can bypass, and the cup turns watery or gritty. The filter is a system, and the porosity is carefully decided. K-Cup coffee looks like drip coffee, but it behaves differently. Water enters through a very small puncture point, not a shower head. Flow is faster, more concentrated, and machine-driven. That's why the grind size, the filter permeability, and internal geometry all have to be tuned together. Too fast, you'll have weak coffee. Too slow, clogging or overflow. Let's talk about the bottom piercing zone. The bottom piercing zone looks trivial, but it's one of the most engineered parts of the pod. It must pierce cleanly, avoid plastic shards, form a predictable outlet, avoid sudden dumping, and maintain stable flow. This is where many of the early patents lived: how the pod is pierced, how the filter is protected, and how the flow is controlled after puncture. In single-serve systems, the boring parts are where the intellectual property hides. This is also why compatible pods vary so much. Two pods can look identical and behave completely differently. Small changes in the plastic stiffness, filter attachment, filter porosity, bottom geometry can lead to big changes in the brew time, strength, and taste. That's why some compatibles are excellent and others are just brown water. Let's talk about compostable K-Cup compatible pods and why they exist. Compostable only works if the disposal infrastructure exists. Many pods are compostable in industrial facilities and not at home. So the challenge isn't just materials, it's system. The industry is still searching for a format that behaves like a K-Cup in the machine and like coffee grounds at the end of life. One of the inventors regrets. One of the most striking facts about K-Cups is that one of the inventors, John Sylvan, later said he wished he never invented them because of all the waste they created. That doesn't erase what the system achieved, but it perfectly captures the central tension of single serve: convenience versus impact. And it's a tension the industry is still trying to resolve. So the next time you see a K-Cup, don't think of it as a plastic cup. It's a miniature brewing system, all designed around flow, not pressure, built for speed and repeatability, and shaped by materials, filters, and piercing geometry. Also grind, that all have to work every single time. In the next episode, maybe we will go even deeper into the genuine versus compatible pods and why sometimes Keurig watery coffee happens and what actually can improve the cup. This has been Engineered Coffee. See you next time. And as I said in the beginning, please subscribe and share if you enjoyed this content.